Hello guys, this is Aliasing. I know I have a series that I abruptly ended, which was talking about the game that I was making in Fennel. But honestly, I got kind of sick of using Fennel because there's no LSP and it's dynamically typed. So there was just so much trial and error, so many program errors that I just had to dig for that it just I'm like, if I'm gonna make something, I want it to be in a statically typed language. I'm done with dynamic languages. Unless I'm just doing like a quick, little thing. I'm done. I don't want to use dynamic languages. I just don't. And if I do have to use one, I want it to have a really solid LSP that can simulate dynamic static typing, right? So like, yeah, I may use Lua again, but that's only because there are Lua LSPs that support type annotations, right? So that's fine by me. Like at the very least, I can check my function signatures, you know, for their accuracy, and find all those static errors. But that's not what I'm here to talk about today. Today, I want to talk about something that I've been cooking up for a long time. And I always thought that this was a good idea ever since I did a little bit of NES development a few years ago. And I've also done some research on like fantasy consoles, like Pico 8 is the one everybody knows, right? Where it's like a game console with hardware limitations, right? Now, most of the limitations of Pico 8 have to do with the amount of graphics you can store, the complexity of the program. I think it uses a program token count as a measure of its complexity, right? And based on the amount of colors you can use, the amount of resolution you can use, the type of sound that you can generate, that kind of thing. But it's running Lua, right? And the Lua is just Lua, right? So it can do anything. People are writing like 3D modeling software in Pico 8 that's like eating up tons of CPU, and nobody really seems to care. Sorry for the yard work going on in the background, but I just think that approach to fantasy consoles is good. It makes for a nice like community. People can share things. I think artists like to have like a preset palette. All this stuff is kind of lined up, but I enjoyed NES development in a lot of ways. But there were things that I didn't enjoy about NES development as well, and I thought, you know, there are certain aspects to computers in general that I think are very interesting. I've always been a big fan of glitches, right, and weird like edge case behaviors. I'm a big fan of how can you squeeze more out of this thing, right? And giving people that challenge. And that's not something you really strongly get with Pico 8. And it is something you get with the NES, but the NES, it's played out. You watch maybe 2 or 3 hours worth of video, like high quality video, maybe like retro game mechanics explained, right? Or read a few like technical documents made by some of the cutting edge NES developers, and you realize like, okay, like other than some like maybe crazy like mapper stuff that you can do, the NES isn't like a super interesting programming challenge. But I think that it is a good like starting point for what I was thinking about, right? Uh, because I want to make something that is a fun challenge, right? Where the results are interesting, but at the same time, I want it to be like kind of educational in the same way as like programming in NES, right? And I want it to be like designed for fun, and for that educational purpose, top to bottom, right? Um, So there are things that I really like the idea of with this project. And for a long time, I've thought about this, right? I've actually made multiple things that were in this vein in the past already. And I'm not going to go into excruciating detail about them, but I've been looking for CPU architecture that I could make, right? A simple CPU architecture that I could make roughly on par with like the old school architectures. What would that look like, right? And how could I make that fun and interesting to program? And so I've been learning about, these old school CPU architectures. I've been learning, I've studied like PDP a little bit and Z80 and 6502 and all this stuff. And I just think that I think I've got it now, right? Like I've made like 4 or 5 of these that probably would work, and they kept on turning into like a Turing target. You know what I mean? Where the computer is hard to program for, and you end up juggling too much. Right? Or if it's not a Turing tar pit, it ends up being too high level, where it's like, okay, yeah, here I have an instruction that reads a byte from memory, modifies it, and then writes that back into memory. Right? I realize that's not a good thing. That's not actually a good thing. So let me explain a little bit what I'm talking about in terms of my design here. So, sorry, got some funny business here. So, when we're thinking about our architecture, right? When we talk about like, okay, so here's an architecture with one instruction, right? Let's say that this is increment a region of memory, or increment, 1 byte of memory rather, right? In 6502. So here's our inc, right? And then here's our low byte of memory, maybe 10, and then here's our high byte of memory, 30, right? So this will increment address 3010. And this has certain things about it that make it a little bit complicated, right? So the first thing about it, like I said, is that its steps break down into 3 things, right? We read, then we modify, and then we write. So if you want to implement a CPU that does this, unless that CPU is very, very simple like the 6502 is, you might be better off creating a second internal instruction set, right? Like a microcode that breaks down this instruction into multiple instructions, right? And I don't want to do that. I want like a load store architecture. I want like a RISC-like architecture where this would actually be 3 instructions, right? Now, one of the reasons why this is an issue is on the NES. If you have a instruction that does all this, it doesn't actually break down just into read, modify, write. It can actually break down into read and then modify and then write, right? Or it can break down into read and then modify and then write, potentially, for the simplicity of the internal implementation of the CPU, right? So there's a layer of abstraction where it's actually obfuscating something about the machine, and the way in which the 6502 does I/O causes a big problem with this. So let's say that you have a device that is memory mapped to address 2020, right? And that's a real like NES address, right? And let's say that this is something that allows you to read and write memory, right? So every time you write to, this is not a real one now, but it's similar to a real one. So let's say that this is our address, right? And then this is our value. So if we want to give data to the GPU or the PPU, right? Let's say we want to put the byte 30 at address 802.0802 of the GPU, right? So what do? So first you would write address 02 to the address, right? So address 2020 is a special address where every time you write to it, it does something, right? So first you write byte 02 to it, then you write byte 08 to it, and now the GPU internally knows, okay, my address is 0802, right? Then you would write your byte to the value register of the GPU, right? By writing to address 2021, right? So when you write to address 2020, it doesn't map it to RAM, right? There's actually like a memory controller, and then that will send data to the GPU, right? That's all great, but here you have these special things where if you do an extra read or an extra write that is not expected, all of a sudden you are going to do something unexpected with this device, right? And that's a flaw of the 6502. You don't want to use certain like read, modify, write instructions on these memory mapped addresses, right? So if we're doing assembly, it shouldn't be a high level assembly, right? It should be a low level assembly. It shouldn't have funny problems to know about like this, right? Like the 6502 was made in an era where, assembly programming itself was meant to be more ergonomic. And so it had these advanced features that I don't necessarily want to have, right? I still want assembly programming to be pleasant for this, and it can be. That's the thing. It actually can be with good design, but I don't want to have that property. The other property of this is you'll notice it's increment, 10, 30, right? So this is a 3-byte instruction. I am a fan of fixed width instructions. I don't like how this hides a different thing, right? Like let's say that this is sitting on the ROM, right? So what this is hiding is that it's not just read, modify, write. It is what? It is, so first it fetches this address, right? So there's a register called the program counter, which acts as a memory address into the ROM or the RAM or wherever you're reading your program from, right? So this is read in the fetch, and then the byte that it fetched is decoded, right? So it decodes it, and then it sees, oh, I decoded this, I have to do another fetch to figure out, this byte, right? It fetches this byte right here. And also this byte right here. So decode and then fetch again, right? And this is all just like adding extra steps and cycles and complexity to the CPU that in a way kind of like obfuscate how the CPU is actually working. And I don't really think it's needed. I don't think it's actually needed. I think, and this is something I realized through a lot of experimentation with different instruction sets, I think you can just have a fixed width instruction set. I don't think you need to have a variable width instruction set. I don't think you need read, modify, write. I think that you can do a load store instruction set. And I think you can do all of this in only 8 bits, right? So 256 possible instructions, just a fixed width 8-bit instruction set, right? Now for reference, like the current sphere of existing instruction sets, there is no fixed width 8-bit instruction set. That's not a thing. It sounds insane because it's like, how do you fit a whole computer into 256 different bytes? This sounds like a Turing tar pit, right? This sounds like, brain fu that language that is just like designed based on like a crazy like Turing machine type configuration with like very few instructions, and it's considered like this fun programming challenge, but it's not used to like make anything in reality. No, I'm not talking about a Turing tar pit. I'm actually talking about a language that is possible to write in, and I would say about as pleasant to write in as 6502, at least provided that you have a decent assembler, right? So let's get into this a little bit, right? So I made a proof of concept fixed with 8-bit instruction set in the past. So I know what I'm doing already, but I wanted to show you the work that I put into it and the thought process and recreate that. So we're going to make the instruction set that I make here in this video into a whole thing, right? I'm going to start with this, but I'm going to make an assembler, I'm going to make an emulator, I'm going to design every feature of this NES-like fantasy console and implement it on video and show that to you, right? So let's think about this, right? We have a 256 instruction machine, right? So our high byte can be what? Anywhere from 0 to 15, and our low byte can be anything from 0 to 15, right? So 15 being F, right? But we don't need to be that specific about it right now. That's not the most important thing. So let's think about this now. Where would you start with this, right? Like, what's the most basic thing you can think of that a computer can do, right? And the most basic thing I can think of is arithmetic, right? Like a calculator. And that is a good way of describing the most basic operations of a computer, right? So what instructions would a computer need to be a calculator, right? Well, the first thing is that it needs registers, right? So this is a fixed width instruction set, meaning that I cannot store numbers in the instruction, right? So like, I can't make an instruction that says add 5, 5. That's not an option for me, right? Because I can't fit all of that data. I would need, with 256 bytes, I wouldn't be able to fit bits. I wouldn't be able to possibilities of 8 bits. 256 possibilities of 8 bits. I can't fit add 5, 5 into an instruction. But what I can do is load 5 into register A, load 5 into register B, right? And then add A and B together. That I can fit in, right? But even then, let's think about how many bits would this take, right? So let's say that load is encoded as 4 bits, right? 0000, but whatever. It's encoded as 4 bits. That only gives us 4 more bits to say what register do we want to load into, right? and what value do we want to load into the register. So yeah, sure, we can fit 5 into 0101, right? We can fit 5 into a single register, into a single nibble, right? But that's not very useful, right? Like, we don't want to only be able to load numbers 0 through 15 and have a 4-bit computer. We wouldn't be happy with that, right? So we want to partially load. So let's think of it this way. Let's free up an extra bit, and say we just use 3 bits to encode the first part of the instruction as a load, right? Or even, let's say that we only use 1 bit. If it starts with 0, it's a load, right? And then we have, okay, which register are we loading into? I think we'll need like at least 4 registers, so we'll add 2 bits for that, right? And then that gives us the chance to have 5 bits. And to load an 8-bit value, you only need 8 bits, right? So now we can think about, okay, we want to load a bigger value into A, right? Like, let's say we want to load hex CO into A. So we would do load high, C into A, and then load low 0 into A. And now A equals C0, right? So this would translate into 2 assembly instructions. And by doing it this way, we actually match the same amount of entropy as the 6502, right? Like, this is composed of, some magic bits, and then, the hex code for C, which I think is 1100, and then some magic bits, and then 0000, right? Whereas with the 6502, you would do like LDA, CO, right? And what does that do? That does, 8 magic bits for LDA, right? And then it does CO, just like that, right? So these are both 2 bytes. So this is actually not that bad, if you think about it. The only downside is, for every single register, we're going to need 2 of these instructions, right? One for load high, one for load low, right? Which would mean if we have 4 registers, which I don't even know if that's enough, that would take up half of our whole instruction set, right? So we would be using up all of this, and that would just be for 4 registers. And these are just for loading basic values into the instruction set, right? That's very, very limiting. But the second observation that I made about this is, wait a minute, instead of load high and load low, usually, like pretty much always, programmers are just loading a single byte, right? Like, they rarely would want to like load a high nibble in, and then load a low nibble in, and then load a low nibble in, and load a high, you don't want to do all that, right? So what if instead of this, you actually had the load operation do this, where, and load is a terrible term because load is used for like loading from memory, right? So this would be like considered load immediate, not just like a load in general. A load in general is reading from memory. We're not there yet. But think about it this way. Imagine we have a load nibble instruction, load nibble C into A, and what it does is it shifts A by 4, right? So if A was 1010, 1010, right? It turns A into, or let's say 1010, 1111, right? It turns A into 1111, 0000, but then it loads nibble C into it. And C happens to be 1100, right? Does that make sense? So it does A shifted over by 4, and then it does A is ORed with C. By doing it this way, you can think of it like we're buffering the data into A. Now we only need one instruction. Load nibble 0 into A, right? So now we can do this all with one instruction. So let's start by filling out load into A, right? A is one of our registers. Load into B. B is one of our registers, right? So load nibble into A. Nice and simple. And then this one, load nibble into B. Now why does this take up a whole row, right? So if you think about the instruction encoding again, we have our 4 magic bits that tells us what instruction it is, right? So 0000 is load a nibble into A, right? And then the other 4 bits are the nibble that we are loading into A, right? Same thing with B, right? Hope that's all clear. But just being able to do this and have an add, right? Add, it doesn't tell us, it doesn't give us very much. So yeah, we can have our load nibble, we can have our add, but really, like, this isn't going to give us a whole computer. It's just a starting point. And I'm going to go over the rest of this fairly quickly because there's a lot to explain as to the design of the 6502. Why is it made this way? You know, all this stuff. So we'll just go over it pretty quickly. So the first thing to think about is here we have an 8-bit add. That's great, but what if we want to add 16 bits? How would you add 16 bits together? And the 6502 solves this problem in a very particular way. So let's imagine for a moment that we add together, right, 4-bit numbers, and we want to make it 8 bits. The same principle applies, right? So let's say we're adding 1000 plus 1000 into a 4-bit register, right? So that would add up to 0000, and then there's an extra 1 here that doesn't fit into the 4-bit register. So what do you do with it? That's where the carry bit comes in, right? So in addition to registers A and B, we'll also add in a carry bit, right? And the carry bit is set to true or 1 if the result of the last addition puts an extra 1 over the edge, right? And this way, if we take this result and we wanted to add, say, another 1000 to it, right? It wouldn't just be 0000 plus 1000. Rather. I'm explaining this wrong. Now let's say that we have our 8-bit number. There we go, right? So our 8-bit number is going to need to rely on this carry bit in our addition. So first we add together the low bits of the number. These are the low bits, right? But let's say our number is 1001000, and we're trying to add 1000 to it, right? So first we added this part to it together, and we found this is 0000, and our carry bit is set to 1, right? Then we would do, for our second add, 100 plus 0000, right? All zeros because there's no, like number here, plus 1, right? Because of our carry bit being set. which gives us the result 101, right? So 101, and that would be the correct result of the binary addition. So we need to have a carry bit. So add is not add anymore. Now add is ADC. Add is add with carry, right? But before we add, how do we know if the carry bit is set or not, right? So this is another thing that we have to put in our instructions. CLC and SEC, these are 6502 instructions. They set and clear the carry bit for additions, right? So if you're only adding 8-bit numbers, you don't care about carry, every time you want to do an addition, you want to put a CLC beforehand, right? In fact, anytime you start an addition that you don't want there to be a carry bit into it, you would put a CLC beforehand, right? And then you can also use SEC and CLC as a hack if you're trying to add one extra to any given addition, but we're not going to worry about that, right? And, well, what else can we do? We also want a subtraction. So we'll have SBC for a subtract with carry. And for various numerical reasons, you want to use SEC to set the carry bit before you do an abstraction, just the inverse of an add, right? And that's just for various like numerical reasons that are related to the number format, right? But what else, you know, what other arithmetic would you want on a CPU? Well, we know that AND, OR, and XOR are all useful, right? These can be used for bit flags, for cryptography. You know, these are all very common bitwise operations, right? And then maybe we also want to think about multiplication, right? Now I'm going to go with the 6502 approach here. Multiplication is not built into the CPU. It's too complicated. But we have a means of doing multiplication, and it's not through repeated addition, but rather through a very similar approach to how we would do a conventional multiplication, just with binary, right? I'm not going to explain that algorithm in this video. I will explain it later in this video series, if you're curious. But in order to do that, we need to be able to do bit shifts, right? And a bit shift is just like multiplying or dividing a number by 2 in a lot of ways, right? But on the 6502, you get 2 different varieties of bit shift, right? So you get, you know, arithmetic shift left, which always shifts in a 0, which is like multiplying by 2. And then we also get rotate left, which rotates in bits, right? And then we also get our arithmetic shift right, rotate right. Okay, so this is looking like all right, but we're still missing a lot of things that the CPU can do. We don't have any memory access. We have like some of the arithmetic tools to do a multiply. So like, let's say, for example, I want to, you know, load in a value and multiply it by 3. So maybe I would load 5 into A, right? And then maybe I would want to think about this a little bit, but maybe we also load 5 into B, right? And then we would shift left B and then add, well, first we clear our carry, right? And then add, right? Now, this is where the instruction set needs to get a little bit more complicated, because all of these are unary operations, right? And I just tried to do a unary operation on B. So how do we tell the computer whether we want to work on A or B? Well, we need to think about that, right? So let's do this. We'll put these unary shifts like this, copy them, right? And I want you to notice that, like, putting things 4 apart, putting things 8 apart, these are only 1 bit difference from each other, right? So this is going to help us a lot, being able to do all this. On A, on A, on A, on B, on B, on B, on B. Right. So this is a program that will, you know, give us 5 times 3. It will give us 15, because 5 times 2 plus 5 is 15. But we have a funny thing here. Why are we loading 5 into A and loading 5 into B as well? That seems a little bit like, you know, well, how do we know what it is? We want it to be generic. We want whatever it is in A to be multiplied by 3, and that's not what we're doing. So we need a way to copy values around, right? And this is what's called the move instruction. So instead of load 5 to A, maybe we do move A to B, right? So now let's think about this. We have 4, we have 2 possible registers right now, A and B. But we're going to need 4. I'll just tell you now, I figured this out beforehand. We're really going to want 4 registers that we can move to one another like freely. It makes everything way better. And those are going to be X and Y registers, which we call the index registers, right? So let's have our move instruction occupy this. We have 4 destinations, and we have, 4 possible sources, right? So this is going to be move, reg. Put that there. The other thing I'm going to do is switch notation. I know this is confusing, right? We like to say load 5 into A. The convention is load A 5, and the convention is move B A that I'm going to go with, which is putting the destination on the left. So we can think of load A5 as A equals 5 in programming, right? So we're just going to switch this off, but you know that load A5 means load 5 into A, right? And also, because it's load immediate, maybe I'll use LI, right? So LI, nibble, LI, nibble. An immediate value is just a value that's sitting there in the ROM in the same place as the instruction itself, right? Now, let's think about another thing that our CPU is going to want to be able to do. That is memory access, right? How would you go about this? So on the 6502, I can just do, STA, say 2030, right? And that turns into what? Here's a magic byte for STA, here's a 20, and then here's a 30. 2030 in hex is why I use the $sign. I'm not trying to do a price. This is just the assembly convention for hex, right? Anyway, you can also do OX if you want. But this turns into this, but we have a fixed width instruction set. So how do we do it, right? We're going to need 2 more registers for the memory address, right? So let's call these L and H. These are the low and high memory addresses, right? So overall, we're going to need 6 registers that we can load into. A, B, X, Y, L, and H, right? And now that we can load things into L and H, right? Now we can think about how we would do loads and stores, right? Because if we have memory addresses, that means that we can load and store the contents of a register into a memory address, right? So we could do load reg here and have that take up 4 instructions so that it can load A, B, X, and Y into the contents of a given, memory location, right? And store reg, maybe we put it here, right? Store reg. Maybe we want to do this, but when we're thinking about this load and store logic, we want to be able to do a little bit more with it, right? Like if we want to have an array, I don't want to continuously be incrementing the memory address, right? Especially since that would currently, as it is, involve, doing like several cycles to add 1 to L, and then if it overflowed, add that into H as well, right? That would be very messy, very inconvenient. So I want to take a feature from the 6502, which is indexed loads and stores, right? And unlike the 6502, on that computer, when you do an indexed store, right? So it would be like, load 2020, comma X, right? So this would take the contents of X, add it to 2020, right? And then index that out of the memory, right? So it would be kind of like doing this. A equals that, right? We don't necessarily want to do just this one thing, because really all this does is allow us to index through 256 bytes of memory, right? Because X is a one byte register, so it can go from 0 to 256. But in modern programming, we can have arbitrarily sized structs, right? So, you don't necessarily want it to just be X. You might also want to do 2X or 4X, right? But right now, if we want, a 2 or 4 or 8 byte struct, we don't have a way of, changing the index register to match that, right? We can't add anything to X. So what would be the best way to do this? Well, we can add, a shift left and a shift right to X for 1, right? That helps a little bit. But let's say that we're also using X as a counter variable, right? Well, now when you've shifted it left to use it as a memory address, you've also screwed up being able to use it as a counter variable. So let's think of it like this. Store into a register, right? And then we have 4 instructions used here, but we have room for some variance. So let's say n times x, right? So HL is our memory address plus n times x. And then this will now take up this whole row, right? So this would be storing 0 times x. This would be storing 1 times x, you know, etc. Right? So that way we can have like a few different sized structs, and that with the shift instructions will allow us to have structs of many arbitrary sizes, which is very nice for modern programming. All right. But the other thing is, like, well, we have a, b, x, and y that we can now store and load memory into a, b, x, and y. But now we can't use y as an index register when we can't use x as an index register when we're storing into x, right? That wouldn't make sense. And we have 2 index registers set up, right? Because I pretty much just copied the 6502. I just found that when I was implementing various like programming algorithms that you wanted to have 2 index registers. It just made things better. It made things simpler to do, right? But we only have room for 2 of them. So we need to find some kind of compromise. And the compromise that I arrived at was that the register can only be A or B with memory operations. If you want to load something into X or Y for memory, just load it into A and then copy that into X, right? Or load it into B and then copy that into X, etc. I just found that being able to use X and Y as index registers really made a big difference in terms of that compromise. And I will say, like, this is part of where we get into the Turing tar pit weeds, you know, because this sort of compromise is not wonderfully elegant, right? But at the same time, like what we were doing before, by being able to, you know, load into register X, right? Say like with these 4 bytes of memory, while using X as an index register, that wouldn't really work, you know, in the first place. And this kind of avoids all of that. The other redundancy that we have, but we don't have that redundancy now. That's good. We really don't want any redundancy. Actually, that's not a redundancy, it's an impossibility, right? So that would have been a space where the implementation gets more complicated, and where somebody who's reading the assembly bytes might read a 6 and then something else is going on. It could be confusing, right? That's not what we want. But the other redundancy that we have right now is, because we have 4 destinations, A, B, X, and Y, for our move instruction, and I suppose that we now would want to be able to also move, you know, move A and B into H and L, so that we can do indirect memory access, right? Where you take the result of a memory access and use that as a pointer, right? So we want to be able to do that as well. So let's add some instructions. Move LA, move LB, move HA, move HB, right? You really only need like 2 of these, but whatever, right? It could be useful to have more. But we have a redundancy with move reg, where if you move a register to itself, it does nothing. This will make sense eventually, right? That I'm leaving that in. Otherwise, I'm very neurotic about not having redundancy. So let's think about this a little bit. How do we make this a real computer at this point? Like, we have a really nice foundation here. How do we make this a real computer? We have to have control flow, right? And that's just the last thing to think about here, right? So we want to jump instruction, right? So this will jump to the address that's stored in HL, right? And what that's really doing is copying the program counter into, HL. But we want to jump, right? But we also want to have conditional branching, right? We want to be able to say, like, if the carry bit is set, do something. But we also want to say if 0 bit is set, do something, right? And I'm realizing now that, maybe these should be over here, right? But I don't know, I have a lot of room to work with right now, in terms of the instruction set, right? So let's make it so that we have our, registers, our A, B, X, Y, PC, program counter, the location in the ROM, and then SP, the stack pointer, right? That's our, that's something we'll have later, actually, right? And then the flags are what? C for carry, now Z for 0, right? So now, if the last thing that was loaded into a register is 0, the Z flag will be set, right? And then we can also add N and V. So the N flag is negative. In other words, that is true if the last time that memory was written to a destination register, if that destination register had its highest bit set, then it's negative. So the N flag would be true. And then the V flag is for overflows. So if you have an add that wraps, it will set the V flag. Or if you have a subtract that wraps, it will set the V flag. And remember that wrapping is a little bit different than carrying because you want the V flag to be set after a subtraction, right? So anyway, the V flag's not that important. Like, I could get rid of it. That's a holdover from 6502, right? It's not used that often, but we definitely want the CZ and N flags, and then we want to have, branch if C is set, right? So that would be BCS, BCC for branch if carry clear, right? Then we have branch if 0. I forget what this one is set to. Oh yeah, it's BEQ, right? So when we do a comparison, if two things are equal, they're considered 0. So BEQ is the 6502 shorthand for that, right? So branch, 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 branch. And then finally, we just want, the N flag set. So BPL for branch if positive, BNA for branch if negative, right? So here's some branching shorthands, right? And the way that the branching works on 6502, I will steal this, is that it uses L as a 1 byte offset to the program counter, right? So it's a number between -128 and 127. It chooses where to go with the program counter, right? So with all of this, we now actually have enough to write a multiply algorithm. We have enough to write a ton of different stuff that you could do on this CPU, on any given CPU. With just this is actually enough to have a functioning CPU. This would be enough to have a fantasy console that you could use. It would be enough to compile for. But we have a funny problem here, which is we can't call subroutines, right? We don't have any subroutine functionality. And this is where the SP register comes into play. So in 6502, there is a stack pointer register, right? There's a stack of up to 256 bytes. And this is used for program execution, because if you think about it, if I'm in a routine, right? So let's say we have our routine A, right? And then we call A on itself like this, right? How does this turn into a computer program, right? It happens that when A needs to, execute, it does what it's going to do, right? And then it returns a value to its caller, which is also A, right? But how does it know what address to jump to when it's returning, right? So a better example might be like B of A, just like this, right? So what is this? First we execute A, right? And then we return to B, right? But in order for the computer to know where is B, where do I return to, it needs to put the return value somewhere, right? The return address somewhere to tell it where to jump to, because if a different routine, C called B, right, then B would still have to return to C, right? So using just plain memory, you can have one address be set as like a designated return value address, but that doesn't work the moment that B needs to call, H, right? Now, the return value for routine A has been overwritten by B, right? And now, when H returns, it'll return to B, but then when B returns, it'll return to itself, right? So how do you solve this problem of return addresses? Now, of course, you can do it manually. You can do crazy compiler, whatever. We're not going to do it that way. The solution is a stack, right? It makes a lot of sense. This is a stack of values, right? The most recent value is the one that's most recently consumed when you return to something. That's why we have a stack, right? And on the 6502, this is done with two instructions. There's JSR to some address, right? That's jump to a subroutine, right? And then there's RTS, which is return, return subroutine, right? So what does JSR do? First, it pushes the PC to the stack, the program counter to the stack, right? Then it jumps to the subroutine address, right? What does RTS do? It pops PC off of stack, right? It returns the program counter from the stack, pops the stack, right? Now in our thing, remember we can't have an explicit instruction for that points to a memory address. So in ours it would be, jumping to the subroutine that's pointed to by HL. But the idea is pretty much the same, right? So now we can add these JSR and RTS subroutine call instructions. They're a little bit high level, they do a lot, but I think that that's pretty sufficient for that. Now what I'm going to do in the subsequent episodes, right? Like this is our very baseline instruction set. This would work to have like a functioning computer, just this. Like this would absolutely be enough. And we have so much open space, right? What I'm going to do in subsequent things is make programs in this, right? Programs in this. And then as I write the programs for this instruction set, I will assemble them by hand and then take that handmade assembly and toss it into an emulator to make sure that it works, right? And figure out as I go what possible changes or adjustments to this instruction set make it more viable, right? What am I currently missing from this instruction set that I should add in? And that will be revealed as we program, right? That's something that is true of instruction sets in general, is that you prove them by using them. It's not immediately obvious based on looking at them whether or not they're good. So in our next video, having made this design, I will implement some basic aspects of it and give it its first really good proving test. So thank you guys so much for watching. Looks like we hit exactly an hour. That's about what I was aiming for. And I hope to see you next time. Bye-bye.